Thank you for coming to our speech-to-text with Elasticsearch conference. I'm Sophie Carboni, and my colleague Lucian Precup, as you know it, is pretty... welcome back. No? Lucian Precup?
Okay, yeah, sorry. Okay, we can hear you well, we can start, yes.
Okay, great. So we want to try to improve what already exists, and we will try to do it with Elasticsearch. So I will let my my colleague Lucian Precup say hello to you.
Thank you. Yeah, so sorry about the small technical difficulties we had earlier. I was saying that, so thank you, Berlin Buzzwords, for having us. Thanks, Atita, for the introduction. And yeah, seeing the pictures in Berlin was really nice. It's as if we were there. So it's great that Berlin Buzzwords managed to gather the community again. So for the second year virtually. And we hope to see you in person in the near future. So yeah, thanks, and let's get going.
Okay, very nice. So surely you may ask yourself, why talk about speech-to-text technology at a search conference? Well, in most search engines nowadays, you may notice a small microphone button on the search bar, like on Google or a lot other search engine. And when you click on it, you can speak out your request, and the search engine will do the rest. It will understand what you say and do the search request for you, and you won't have anything else to do. It's really, really useful and really practical.
Other vendors like Algolia, for example, also released a voice search, and they actually made a they made a poll, and they estimate that 71% of people prefer searching through voice than searching through keyboard. So yeah, it's something that's coming, and that will come a lot more. We also have added voice search to our collaborative search engine, which is called All. And speaking about Elasticsearch, we also have a search engine that you can find at this address, that hopefully will have a voice search in a few days. So the voice search will go into production in the next days. If you want to search through resources that are available for Elasticsearch developers and Elasticsearch developers using your voice, you can go ahead.
So we tried out some speech-to-text technology available today in the Meet application. You may know it. It's from Google. In the Meet application, for example, if you go and do a video chat, you just have to enable the caption feature, say which language you are speaking on, and as soon as you speak, it will transcribe everything that you say. And it works pretty well. As you can see, we were saying. I can't see. I'm sorry.
Yeah, so Google literally translated what we said. So it translates. Yeah. I mean, it translates, yeah, into text live as we speak. Yeah. You just have to click the captions button, and there we were saying that technologies around speech to text are really powerful today. Yeah, so you also have the recognition of the speaker and all that. So it's really, really powerful.
Yeah, it was really fast and really accurate.
The technology evolved a lot in the last 2 years, and so you can see the microphone button almost being in a lot of places, but still, if you open the previous websites that we showed in Firefox, for example, you will notice that the microphone button is not present. So actually, there's kind of a disruption there. So if you're using Chrome, Android, or Microsoft Edge, okay, you have the technology that's enabled, and usually it is enabled with cloud services that are available by Google or Microsoft or AWS.
So you have to have an internet connection to use this speech-to-text engine. It's you don't have full control over what happened with your data.
So speaking about open source, there is technology available in open source, and it evolved a lot in the last 2 years, really. Here we give some examples. So Kaldi is used a lot in mobile devices, on Android, in applications, so that you can build on mobile. Vosk API is built on top of Kaldi, and it's really powerful. You can also use it on very small devices. It works offline without internet connection. And we also cited CMU Sphinx, which is kind of obsolete today, but it has some pretty neat features that we will also use during our demo. And I think I think it's time for a short demo, or am I mistaken?
I don't think so.
No. There's also there's also an initiative from Mozilla called Deep Speech. So it's using machine learning, as you can imagine. And Mozilla also has a project called Common Voice, where you can donate your voice for a database that is used then to teach, to learn, to construct the models that are necessary for this technology to work. You might also know that you're already donating your voice to Google and Amazon and Microsoft. So Mozilla also does that, but you have to go to their website and read a text and
consent.
do something for good. Yes.
And here's a demo.
Okay. Yes. So we will show this directly. So it's a demo of Vosk API that we have prepared just to show you how powerful the technology is. It's at least as powerful as what Google had to translate. So I don't know if the organizer, you can switch to my screen here. Yeah. Okay. Great. So everything is powered by a Apache licensed model, which is really small. It has less than 50 megabytes, and it fits on a mobile device. As I said, it works without an internet connection. It works really locally, and you will notice that you just have to install that to run it, and you will notice that it will actually capture what you say and will translate that into text. So as I speak, the text will appear on the screen. I hope the refresh rate is
it's
good enough so you can see. And you can see that it's really, really accurate. All that with just a 50 megabytes model. Okay, we even tried something. I hope it works. You can even, for example, sing.
Before you came around, I was doing just fine. Usually, I don't pay no mind. And when it came down, I was looking in your eyes. Suddenly, I could feel it inside.
Okay, so that's the demo effect. There's a lag there. It usually works. It depends where the sound is and all that. But this technology is also capable of identifying the words that are in a song. So you imagine the difficulty of doing that because you have a lot of noise, which is not voice, which is something else, and you have to get through that and figure out what's being told. Okay, so I'll just stop the demo here and we'll move on with the presentation. Yeah, so how does it work? So pretty simple, simple. I mean, it's based on machine learning, as we said, and it needs a lot of training data. So this is why the Common Voice project from Mozilla, you actually need to train models, and the key point in the technology is that you can. So you train the model. So the model should be, if the model is trained correctly, then you get something really accurate. And you have to do iterations to train and retrain, to check, recheck, update, and then learn and generate.
You have to prepare recording and their word transcription, and with deep learning you will make a liaison with the transcription and the recording, and the more data you get like this, the more accuracy you get as a result when you try speech to text. Speech to text.
Yes. Now we will get back to the demo again. So sorry, we switched screens like this because we are kind of presenting this together. So here's again the demo. And we will do something else. I will show you something that happens when you plug the wrong model. Okay, so here I will plug a different model, which is, it happens to be a great model, but it's trained for French. Okay, so I'll just plug it here. And we run the test again. And you will see what happens. I think yeah, the screen sharing is interfering with my computer, but and this is why the translation of the song earlier didn't work. But as you can see, what's been translated to the screen has nothing to do with what I say, and that's because we have the wrong model. The model is not trained in the right conditions. The model is trained for something else, which happens to be French, and I'm speaking English right now. So you can, there are words that are displaying, but they don't mean anything because it's not what I just said. So yes, I'll stop this again here. And we'll get back to the presentation.
And if you think that Google does better because it's Google, no, it doesn't do better. We tried the same thing as earlier with the software Meet, and we tried to put the caption on, and we said that we were talking in French while we were still talking in English, and the result was totally irrelevant. We said exactly the same thing as earlier, and as you can see, the result doesn't make sense. Maybe you don't speak French, but even in French, it doesn't make sense.
Yeah, so this is not connected to the fact that it's an open source technology that is a small model. This happens even with Google. So if you plug the wrong model, then the result is not really, it's not great. I mean, it's irrelevant. And this brings us to something that we would like to solve, and this is what we will show you in this presentation. So in the song that you heard earlier, there are actually two voices. You have Dua Lipa that speaks English, and you have Angel that speaks French. And actually, this is a situation that you see often in some circumstances. For example, if you're in a meeting, if you work in Belgium, in a meeting, you can hear Flemish, you can hear French, and you can hear English in the same time. Yeah, it's it happens there. And you can also, yeah, if you are with your friends, if you are with your kids, you might speak a language with your kids and they answer in their mother's language. And this is a common situation, at least in Europe.
Yeah.
So we said, how about we try fixing this with Elasticsearch? So in order to do that, what we did, we first took a step back and said, okay, before machine learning, how did things work? So actually, there's something before words, before the words that you have in a certain language, which is called phones. So actually, the speech recognition technologies will first recognize phones. So yeah, you speak, the microphone will detect waves, then you will have phones, and starting with these phones, you will try to figure out what were the words that you have been saying. So this kind of seeing things, this way of seeing things would allow us to have something like a, let's say, universal language that's not English, that's not French, that's not German, it's simply phones.
So phones are the most basic unity of phones that you can do when you say a word, like the phones E, the phones P, things like that. Very small unity of sounds, and there exist some codes that describe this kind of sounds. You may recognize in the first line the IPA alphabet, which is for International Phonetic Alphabet. It's widely used when you try to learn a foreign language from your home language. You will have words that are written with a letter, like in the left side of the slide. And on the right side on the slide, you have the exact same word, but written with its IPA transcription. And when you try to pronounce Berlin buzzwords while reading the letter, you write you speak according to the pronunciation that is described by the IPA transcription on the right. You can see that we have the three first lines that use IPA, and the three lines below are using alphabet. Alphabet is a set of code to describe phones too. So it's not an alphabet, but it's kind of the same. And if you try to read the alphabet transcription, you will see that it's pretty intuitive. If you try to say what is written on the right of Berlin buzzword on the below of the on the bottom of the slide, you will see that as you speak, it looks like Berlin buzzword, what you meant to say as words. And it's pretty intuitive. And it's what we chose to use for our prototype, because it was what CMU Sphinx used. And since we use CMU Sphinx, it was more practical to use alphabets than IPA.
Feels like going back to school. The translation there that you have in IPA, it's like the phones that you have seen in school, and it can even allow you to learn German or French, because you have the way the sound is pronounced and not the way it's written.
Yeah, it's
so
international. So here are some reference. Oh, sorry.
Yeah, no, go ahead.
Okay, it's some reference that you can see later if you are interested about what we said about IPA, CMU Sphinx, and alphabet. And here, the next demo.
And we will switch again to a new demo. Just before going to that, just to explain you what we did and how does this work. So we actually took the spell check dictionary from OpenOffice. It is the same one that's used in Firefox. You have dictionaries that are available and freely available in open source for a lot of languages. So we took the English one, the French one, and the German one. And then we translated these, the words that are present in these dictionaries into IPA. You can also find dictionaries translations like this pretty easily. I think even Wikidata shows how each word is pronounced. So it's pretty easy to find. But we also needed to translate that into the CMU pronouncing dictionary, because for our prototype it was easier, and it's a notation that works better for us. You will understand why when you see the demo. So this was the third step. And
so alphabet, you said CMU dictionary, but it's alphabet.
Yeah, it's alphabet. Yes.
Yeah.
Then with this, we created indices in Elasticsearch. We created 3 of them. And with some specific Elasticsearch queries, we gathered some statistics, and you will understand why. I will switch now to my Elasticsearch demo. So here it is. Okay, so the three indices that you see here contain for French 60,000 words, for English 40,000 words, and for German 42,000 words. As you can see, French are more verbose, and the dictionary looks like this. You have the word, which is the one in the dictionary, and then you have the alphabet translation of the word. For example, here it's written à côté. Okay, so yeah, pretty straightforward. You can even learn French with that. À côté. Okay, so this is the first part. Then I will show you how the index is created. So we actually calculated combinations of 2 phones, right, one next to the other. So we did it with a shingle analyzer. Or maybe before that, I will show you why we did that and what we are trying to get from here. So here are the phones by frequency in English. So for example, in English, the sound a is the most frequent one. The sound n is the next frequent one. Okay. You also have combination of 2 phones, like for this one, a, n, an, al, that are the most frequent in English. So yeah, I go back to the mapping here just to show you how we did that. So we use a shingle filter that will calculate these 2 together. We use also or maybe I show you the mapping first. So the shingle calculates the combination. To calculate the first sound of each word, we used a limit analyzer, and to calculate the last sound of each word, we used this is not really straightforward, so we had to use some more filters here. Yeah, if you want to go into details, you'll know what this means, but this is just to calculate the last phone of each word. And here's what we found. So for example, for French, so you have seen the phones by frequency in English. For example, for French, if you take a look at that, you see that the last sound, it's often A, so it's the sound A, which is the most common last sound. And you also have N, okay, which is also quite often as the last sound in one word in French. On the combinations, so you have these ones. And the first sound in French, the most common first sound in French is A. And the second one, this is really specific to French, is K, 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 okay? So what do we do with this? So here you have the same thing in English. You will see that it's pretty different. The last sound is N, the one, Y also, I. The combinations are not exactly the same, even if they kind of are kind of similar. And the first sound is S and K also. Okay, same for German, and this gives us these tables that Sophie will show.
Yeah. So once we have all the data, we organize them to make a kind of statistical model, like there exists in other domains to identify other kind of data. So in the column, you have the phones that are in the first part of a phone couple. And in the row side, you have the second part of the phone couple. You can see there is space as the first column and first row. It's when the phones are identified as a first phone or last phone. So yeah, you will see that better later. So for example, if we have the couple AHN, which is very frequent in English. It's the most frequent in English. Like you can see in the word abundance, N. You can see that with this kind of pronunciation, it's most likely to be English since it's the most frequent couple of phones in English. But we have done the same with German, and as you can see, the model are completely different. You see that the red represents the most unlikely phone couples, and it's very different in German as it is from English, and even different than it is in French. And for German, for example, the most common end of a word is with the phone N, like in willkommen, for example. It's very common to find words that end with an N in German. And in French, the most common is the sound AAN, which look a bit like AHN in English, but is slightly different, like you can see in the word abonnement. And all this information, all this data are quite the identification of language and allow us with a bunch of phones to identify if it's more likely to be French, more likely to be German, more likely to be English, because of the phone occurrence and the phone couples. For example, if we have the sound if we have the following phones, then we don't know exactly which word it is, which language it's from. We make a map of everything, every font pronounced, and a map of every couple of fonts pronounced, and we see if it's more likely to be English, more likely to be French or German. And as you can see, a word beginning by the sound B is very likely to be an English word, less likely to be a German word. But if you do that with all the font couple of this word and all the possibility of this word, you can see in the end that it's most likely to be a German word than in an English word or a French word. And if you have context, if you have fun around those fonts, it's even more easier to find if it's a German sentence or a French sentence or an English sentence. So in this case, it was the word befinden, which is a German word. So our statistical model helped us to find the language and then the word. In this other example, with the word buzzwords, as you can see, it's most unlikely to be in any language that we have, but there is a lot of 1% of chance of this couple phoneme in French, in German for most phonemes. There is even 0% of chance for the combination ZW, which, according to our data, which are not complete, obviously, is completely unlikely to be German. We don't have a word in our database that has this combination.
This was a complicated word, so we chose it on purpose. But as you can see, it's a word which is not common in any language, but it is a word. It is in the dictionary, and we are happy to be here.
Yeah. So in this case, the context would greatly help find out which kind of language it's from. So in this case, it's English. It's a buzzword, as you can see.
Yes. So we don't have much time. I will go really quickly on this. So just to show you how it goes afterwards. Now we plugged another technology. So I don't know if it's displaying. Okay, great. Which is called CMU Sphinx, and we tweaked it to display phones. So just bear with me. It will start. It takes a little time to start, and I think that the data stream here slows down my computer a little bit. So this technology is like less advanced than the previous one, but it will actually allow us to translate the voice into phones, and then we will be able to, out of these phones, we will be able to say what was the language that we have spoken into and what was the word. Okay, so as you can see, as I speak, you have phones that are displaying here. So it's the line that hypothesis, so maybe it goes too fast, but these are the phones that I'm pronouncing right now. And I will go a little slower on this, and you will recognize the phones there, okay? 5, 6, 7, 8, 9. Okay, so I'll pause here. It had some problem with 8, but yeah, nevertheless, you can see the 5 here. You can see the 6. You can see the 7, etc. So now let me start again. Sorry about that. I needed to pause just to show you that it's actually the same model, the same technology. We didn't change anything. Yeah, there's no one else on my computer while I stopped the program and all that. And I will this time speak. So it's the same model. I will speak in French this time, and we'll see how it goes. And actually, I will say the same thing. 5, 6, 7, 8, 9. Okay, let me pause here again. So you find the phoneme here. So this is 9. This is 8. This is 5. And let me show how we are going to use that. I will just switch again to Kibana. So here it is. Yes. Let me just scroll back. Okay, so here is the phones that we have seen for 5 written in French. So actually, I will query all the dictionaries, and I'll just place there the phones. And here it is. I have the word. Okay, and the same goes with, for example, if I use the same. So okay, I query all the dictionaries, the English one. So this one is, well, the demo effect. So this one is supposed to be cis, but it's actually also an English word, cis. It is pronounced the same. So in this case, it's more difficult. We even have a German word that kind of has the same phones in it. But yeah, this way you see the limitation of the of the thing. So yeah, it works pretty well in most of the cases, and it works pretty well if you have more than one word, so the speech continues.
Mm.
So I think we'll stop here because we don't have any more time. I'll stop here with the demo at least. I think we have. Do we have some more slides, or we are done? No,
Just
we are done.
The conclusion.
Thanks for listening. Thanks for coming, for being here.
Just the last word. Just the last word. So the technology today is really powerful and will continue making a lot of progress in the next few years. It's really lively. We'll try to fix the hard-coded model dependency to a language by using international phones and then dictionary to translate it to words. There is other solution to do so, but here was one potential way. So thank you for listening.
Yeah. So yeah. Thanks for this. And the right solution might be, for example, that to have this kind of universal language where the model is trained to display phones and not words in a language, and out of these phones we can then easily figure out what language that was and even what words that they were.